Hi everyone. In this lesson, we'll be going through Archimedes' formulas. So, in the beginning of the course, we saw some initial relationships between the circle, the sphere, and the various formulas there. And we've kind of worked through some of the actual rules. So, as you can see, we have this kind of little table, just kind of a cheat sheet for how to take a sequence of changes that are sort of all interacting and figure out what the total would be. And so, using this table, we can actually work through the formulas that we saw earlier. So if you remember, we had this sort of intuitive description of what was happening, right? We can start with circumference, we can do a time lapse, turn it into area, take that, thicken it up, make it a bunch of plates, we have volume, then we can sort of take a shell, and then we get surface area. And so this is sort of a very intuitive description of what we want, but using these rules up here, we can actually turn that kind of gut intuition into actual formulas, and the rules kind of help us crank through. Now, the advantage of taking kind of abstract rules like this is that we don't need to visualize everything. It does help to do it, but the rules will work on symbols. So if we can express the shapes as symbols, then we can let the rules do their magic. So let's kind of dive into it. The first step is actually taking circumference into area. And we actually did this on our own with the circle to the ring triangle, right? We took the circle, broke it up into a bunch of rings, and then unrolled it and measured the area. Well, using the equations, we can actually do the same thing, and we don't need to do as much visualization. So the way we'd write it is area equals the integral from 0 to r of 2 pi r, and then dr is the width. So what that's saying is that we have the area of a circle. We can also measure it as sort of the integral from the center outward, 0 to r, and the size of each step that we want to take is 2 pi r times dr. So dr is the thickness there, that little piece, and 2 pi r is the height. So assuming we can actually write down a single step, just this 2 pi r dr, then we can integrate it from 0 to r using the rules of calculus. And in the article, we can walk through it, and we realize that we get pi r squared. And I guess I'll hop in here. It's because the integral of r is 1/2 r squared. And we can check that, right? Because the derivative, well, the 2 comes down, and that cancels this. So the derivative is r. So that means the integral is 1/2 r squared. So we can sort of plug that in, and we get the same answer that we did with the ring triangle. But again, we just were able to use the actual equations, and we didn't have to try to, actually visualize the rings unfolding and measure the area. So we got the first result that we had before. Let's hop into the next one, turning area into volume. Now, our general strategy here is to actually imagine a sphere as a bunch of plates. And what we want to do is sort of add up the thickness of the plates and kind of make our total sphere. So let's take a look. Now, the tricky thing here is how big is each plate? Well, one thing we can do is use the Pythagorean theorem to kind of figure it out. So if you imagine looking at the sphere kind of sideways, we have the x-axis going through the middle. And if we're at some position, let's say, this far on the x-axis, well, if this is our x-coordinate, we have some y-coordinate, which is our height. I don't know what it is, but let's just call it y. We have our width, we have our height, and then by the Pythagorean theorem, we have the radius here, because it's still making a circle. So we have x squared plus y squared equals r squared. And this is just the Pythagorean theorem. We have our width, we have our height, and then we have kind of the hypotenuse, the diagonal. And using that, we can actually rearrange and get the height as the square root of r squared minus x squared. It's a little bit easier to follow in the actual post, but we can just talk through it. So what we have is each plate has a thickness of dx and some kind of height, right? The height is y, and we can leave it as y or we can plug it in. And the area of this plate is pi y squared. Again, y is just the height of it. So we have kind of, pi r squared for the area of a circle, pi y squared because y is the height here, and then dx is the thickness. So that's sort of the general approach of how we're going to take our sphere and cut it into slices of size, dx wide and pi y squared is the area. Now, one little trick here is that instead of trying to figure out the area all at once, let's split it into 2 halves. So instead of trying to get the area of the total, let's just get the area of 1/2 and then just double it. The reason we want to do that is because if we have something that's going along the x-axis, we can imagine the middle of the x-axis is 0, and we want to go from 0 to x instead of having to go from negative x to positive x. And the reason, again, is just it's kind of annoying to deal with all these negative signs flying around. It's just easy and simple to have 0 as the center and go out to x, and then we can double the final result. So when we actually work through it, it's a little bit tricky, and we get a lot of formulas, but we can walk through it at a high level. The volume is basically double the size of 1/2. And the size of 1/2 is the integral from 0 to r, from 0 all the way to the maximum, of pi y squared dx. Now this is, there's a lot of variables here. Let's walk through it. Y is just the height. And again, we can plug in eventually, but let's just call the height y. X is the current position. So we're actually moving from the center, x equals 0, all the way to the maximum, where x equals r. So we're writing 0 to r. Now I could have written x equals 0 to x equals r, but that's sort of implied because we're taking steps along dx here. So that's again another shortcut. We could write x equals 0 to x equals r, or just write 0 and r at the top here. And in the post, again, we can walk through the equations. We'll just take a quick high-level look here. The first thing we can do is take pi y squared. We can substitute in y because we have the Pythagorean theorem over here. We can plug in, what y should be nicely because there's a squared here and a square root. They cancel. So we get a much easier integral, which is the integral from 0 to r of r squared minus x squared, and then times dx. Again, this is the entire size of the step. There's always that dx thickness kind of that we need to account for. And if we use the integral of, in this case, the integral of r squared, r is just a constant. R is just something like 15 inches. It's just a number that we want to go up to. And so when you take the integral, it's just r squared times x, because we're taking steps of x. Now x squared, well, that's a kind of a variable. So when we take the integral of that, we get 1/3 x cubed because of the power rule. And you can double check that. Take the derivative of this, 1/3 x cubed, and we get x squared because the 3 and the 1/3 cancel. So that's, again, a quick way to make sure that you took the right derivative. We can sort of do out the algebra here. We plug in r for x. So basically, this equation will let us find the area of a sphere going up to any x. So we could actually go from the middle to about halfway, or 3/4 to the end, but we actually want to go all the way to the end. So what we're going to do is plug in r as the final value of x. And when we do that, plug it in, we do out a little bit of subtraction, and we get 4/3 pi r cubed. Again, it's a little bit easier to follow step by step in the article, but you can see that it's not too bad. This is actually a very, very difficult formula. Archimedes worked really hard to figure this out, and he had it actually put on his grave because, it was such a result he was proud of. And we figured it out in about 6 steps. Not bad, right? We just did a couple of substitutions and, a little integral right here to double check, and we figured it out. So we actually worked through one of Archimedes' most prized results just in a few lines because we knew about this calculus technique. So I don't know, I think it's pretty neat. Let's jump into the last little bit here. How to find the volume into surface area. So we'll look back up here. We have volume. If we break it into shells and we take one of those shells, well, that should be the surface area because it's kind of the thin peel that's surrounding the volume. So let's just hop all the way down. And the kind of intuition here is the following. If we take a little segment of volume, right, that orange peel that's surrounding it, and we know the size of that peel, the actual volume of that peel, and then we divide by the thickness, that should give us the surface area. And the way I think about it is, well, if area times thickness equals volume, right? So you imagine you have the amount of area, you thicken it up, that'll give you volume. Well, if you take volume, divide by the thickness, then you should get area back. So that's sort of how we can actually get the actual amount of surface area. We take the little segment of volume that we have, divide by the thickness, and now we have the area of that volume. And so in that case, the new area of that volume is dV, the thickness is dr. So that ratio, dV dr, is actually the surface area. And hey, that's just the derivative. We can figure that out. So we can plug it in. The derivative of volume with respect to r is, okay, d over dr of 4/3 pi r cubed. Again, we found 4/3 pi r cubed in the step before. And this is a pretty quick computation. We can just take the derivative, and it plugs into 4 pi r squared because the r cubed comes down, cancels with the 3, and then we just get 4 pi r squared. So it's a really quick computation. That's a one-liner to figure out this pretty cool result. I think, again, that's pretty amazing. Archimedes had to do a lot of work to figure this out, and with the rules of calculus, you just crunch through it really, really quickly. So, at a high level, what have we done? In one respect, we've actually gone through, I consider it 2,000 years of math in an afternoon. These results, to take it to this level and to work through it this quickly, it was literally millennia of thinking in order to actually have a way to break shapes down and to think about them and to describe them in a way that you could actually jump through this entire series in just a few minutes. Once you know the rules of calculus, it's maybe 2 or 3 minutes per step just to go through it. And it's amazing because the greatest geniuses of all time, work their entire lives to figure out these results that you can do on your own. And again, we're not super familiar with them. We're still learning. We're still building our intuition, but you can at least see the steps that have to take place. And even if you can't immediately write down the symbols, you can at least visualize what you're trying to do. And that's such a huge step that, again, took humans, many millennia to figure out. So at a high level, I hope you've enjoyed what you've seen so far, and I hope that the analogies of calculus are starting to click. The main ones, again, not even talking about math and equations and things like that, the main analogies are that kind of X-ray and time-lapse vision, and even more generally, it's about breaking things down into pieces and just looking at that pattern, or trying to find the source behind something. So, in the real world, if you're planning something, can you break it down into little steps and just see if there's a pattern in how things are going to progress? Or if you're observing something, can you try to find the original source that's making that observation? So if you're seeing, a certain phenomenon, can you work backwards and figure out what was actually causing it? And that's the kind of metaphor that calculus thinking can help you kind of incorporate into your everyday life. So with that, we'll be in the future going into some more detailed, variations of calculus, talking about infinity. There's a few more integration rules that we can talk about. But at a high level, I hope you've understood the key insights behind the subject. Happy math.